Okay, section 3 of chapter 20. J.J. Thomson's discovery of the electron gave us the plum pudding model, but his model was completely disproved by the evidence from Rutherford's alpha scattering practical. Okay, and his discovery done by his students was, you can see from my change diagram, my nucleus has now shrunk, but that tiny nucleus has such a huge effect. Particles that go anywhere near it are shot out of the way. These alpha particles, of course, are not deflected by these tinier, much tinier electrons. In fact, the electrons tend to get shoved out of the way as these come bulldozing their way through. But there's enough mass, the whole of the mass of gold atoms, which is much more massive than the alpha particles. So even though they were travelling fast, these were deflected back if they were heading towards the nucleus, but they never got to the nucleus. So how big actually is a nucleus? What's a nucleus made of? We need to go into more depth. And this is where section 3 comes in. So there are different ways, different better ways of finding about the size of a nucleus. Okay, so we accelerate particles. We haven't really changed that, but what we're accelerating can give us different effects. So alpha particles have a problem. I mentioned them last lesson. We're going to look at electrons. Now electrons come into a different group called leptons. They are not affected by the forces within the nucleus. Okay, so these, or the key nuclear force. So these can be used and are still used to do a lot of research. Even better, we can use neutrons, which work in a different way. However, they're quite difficult to accelerate. So, also difficult to explain how to accelerate. So we're going to just stick with what we were doing in electricity and the magnetism topic, which was mainly firing electrons at a particle. Now, we mentioned wave-particle duality last year as our final section of quantum mechanics. This is the idea of what's going on here. So if we fire electrons at it, if we make them fast enough, we know from the mathematics then that can cause us a pattern. Effectively, what we're looking at is if we take a nice thin sample, then the spacing of the atoms within it doesn't need to be gold now, it can be anything. The spacing of the atoms within it means that our electrons effectively change or behave differently. So as our electrons fly in, they behave like waves, and what we get is that beautiful diffraction pattern caused by the spacing. If the spacing is about the same size as the wavelength, so we need to get the right speed, right velocity of electrons to get the right size of wavelength, so you get a nice diffraction effect and therefore you get a nice pattern. Okay, now when we did the work last year, we treated everything like it was a double slit, which is fine up to a point, except that gave us a very clear pattern. Now if you do this, and you can do this with light, you can do this with sound, but if you do it around round objects, you get a slightly different pattern. They fade in and out, they don't actually disappear. Okay, so constructive interference still, destructive, but that central bright fringe still brightest but never fades to zero, and this is what we're getting here. So here is our destructive interference, here's our first bright fringe, and it decays away really quickly. But it gives a very similar pattern to diffraction of light. Why? Because we're diffracting electrons. Okay, so the mathematics of it is very similar. It's just for light. Okay, we had n lambda equals d sine theta. Okay, so we did that a little bit last year, but we did it more with the astrophysics. Slightly different here, and what we'll get for a round object, which is what a nucleus effectively is pretty much, then again from experimentation you can get a value of not 1 to the first fringe or points or halfway to give you that one. What you've actually got is 1.22 lambda equals d sine theta. Okay, and that's for a round object, whatever the round object is. So sharp objects, sharp slits, we get n lambda, and we can see lots of fringes. They're quite hard to see, but if we're looking at atoms, because they're shaped, we'll end up with a slightly different multiplying factor. So that gives us our first fringe there. What we tend to measure is, because that's quite blobby, again, like nodes, it's easier to measure a node rather than the antinode, that wide lump. So we'll tend to measure that. So to use that, again, rearrange it just to make it a bit easier and a bit less maths to do. So for that minimum angle, what you'll find is it's basically half. This is not a great diagram. So we take as 0.61 lambda over r, where r is the radius of our atom. Okay, so basing it down slightly, through experimentation with large scale objects, we can get the mass that we can use for small scale objects, like thus. So we've done the maths that goes with this. Redo it a second, but how do we make that all work? Well, we just need to make sure we have the right wavelength. And as it says there, that's the de Broglie wavelength of particles, in this case electrons. If we change the particle, we'll change the wavelength. Okay. But how do we find it? Well, normally in a class I'd get you to do this, so you can work it backwards. And again, I'm going to stick with E rather than Q. So kinetic energy, or work done to give it that kinetic energy, half mv squared. Okay, so just clear it up a little bit. You'll find it a little bit easier if we make it 2ev equals mv squared. Now, what we tend to need is momentum. Okay, if we go back to where you had your equations from year 1, so year 12, I'm just going to find it. Here we go. So if we look in our wave-particle duality, momentum. Okay, so Planck's constant, which will make a lot of appearances this time, Planck's constant divided by momentum. So mv, but what we've actually got is mv squared. So if I multiply both sides by m, then we'll end up with mv m squared v squared. Make it more convenient, let's do it like that. Okay, so where we had that mass, again, it's not on the data sheet, it just says P, but just remind you, P is momentum, lowercase p, not capital for pressure. That's going to equal the square root of all this, 2mev. Okay, again, v is voltage, not velocity. That's my little v for velocity. So if we want to do the maths of it, how do we find the wavelength? Well, it's what we had before. So P equals h over what I've just had there. Okay, not in the data book. Okay, he says quickly checking. I'm pretty sure it's not in the data book, but it is a crucial little idea to make it all work. Okay. No, it's not. So you will need to be able to work that through. Okay. Yeah, it's not in electric fields either. So you will need to work that through, because that's one of our crucial, that bit through. That's one of the crucial bits you'll need to know. So learn that step. Okay. So, one little thing to keep in the back of your mind, this does not always keep working. Okay, if you get up to large velocities, then what we end up with is something changing about the mass. We get relativity kicking in. So for the mass to be the correct mass, the mass that's we've written down at the start of the chapter, for example, then that has to be what we call its rest mass. So it needs to not necessarily be stood still, but it doesn't need to be moving too fast. So just put a little footnote in here underneath, NB. at hundreds, very technical, of mega electron volts, okay, of energy, then that changes fine, okay? So this is all for this value. Oops, sorry. Then it's valid. But at high energy, M changes with relativity. Now we don't go into that, but basically there is a multiplying factor called the Lorentz factor, which changes that mass. So just to give you a little bit more to go with it, if I can find a pen to write on it, there we go. What you'll find is that the mass changes from the proper mass, the rest mass, by a factor of 1 minus v squared over c squared. Okay, and what happens is, as this velocity gets close to the speed of light, then this squared becomes noticeable. It becomes a reasonably large, well, reasonably small number, and then you subtract that off. So that affects the multiplying factor for this. Okay, so you will find that I've done that the wrong way around. That's for length contraction. So it will be multiplied by that, and it will give you the mass, and the mass will change with velocity. But when you're looking at, say, I don't know, a tenth of the speed of light, well, a tenth squared is 100th. 1 minus 100th, 99 out of 100, square root, it's almost no difference. Okay, but when you're starting to get to, say, 20% of the speed of light, it becomes big. Okay, it actually has a big effect. So that's one of the kind of crucial ideas. What does it lead to? Well, we'll go into the mathematics on that, and that is in your data sheet, so that's quite common. But just to point out, there are different ways of scattering these things. So again, they are talking about different levels of energy, different speeds. We will look at some of these again because they are used nowadays in medical research. There's quite a lot of radiography stuff that we look at the medical imaging section at the end, which involves X-ray scattering, not just X-rays, but X-ray scattering, electron scattering. That whole idea of spreading out is what we're saying with scattering. Okay, and more difficultly, for difficult practical reasons, neutron scattering as well. Okay, so neutron therapy, as you're well aware, I'm sure, is used a lot. Okay, where does this lead to? Well, it leads us into something quite profound, really basic, but quite profound. What they found was, by doing lots of experiments with lots of different atoms, they managed to start to get a pattern, as you'd expect. Okay, and what they found was, they basically found that the radius of atoms is proportional to the cube of the atomic number, okay, the nucleon number. So it was given a value. I should say R0 is not well known, it's approximate. So again, it's one of those questions where people tend to use ratios. Okay, so we are given that value in the exam. Okay, I think they use little case, to be honest, but there we go. But yeah, you'll be asked to compare two sides of nucleus. Again, not atoms, because they won't diffract around the electrons moving around, they just around that solid nucleus in the middle. Okay, and that was found to be a to the power of a third, or the cube root of a. Does that make sense? Well, yes, it does if we think about it. If we do it in a more useful way, r cubed is proportional to a. Now, if we plot r cubed against a, we'll get a straight line gradient. Okay, the one that's given in the exam is this one here, which doesn't quite reach 0. There we go. Which is an x cubed taper graph. Okay, x cubed type of graph, re-say that. And it shoots up very quickly. But it was originally found by working through the straight line through the origin, etc., to find this multiplying value. It's not quite true that the value changes when you get to smaller nuclei. Why? Because this gives us a hint. Excuse me. This gives me a hint of the shape of the nucleus itself. Okay, so we've talked about radius, but is it? Well, yeah, if we think about A, effectively that's how many particles you've got in the nucleus. Effectively that's the volume of the nucleus. If the volume is a sphere, then it will be proportional to r cubed. Okay, so volume of sphere, as you well know, is in the front data book. If you don't, 4/3 pi r cubed. Okay, so our volume, our amount of substance in the middle, number of nucleons, is proportional to r cubed. Okay, so what that tells us is that basically all nuclei, larger nuclei to be fair, but all nuclei are spherical. So why are they spherical? How does that work? What's keeping them together? That then leads us into a whole next layer of questions. Okay, so yeah, just before we move on, just put a little NB. So for exams, you'll often compare ANO atom, another atom, as a ratio. Okay, so you don't need to know the value of that. You can just do radius 1 over radius 2 equals a to the third 1 over a to the third 2. Okay, or if you prefer that version, but the bit in the data book, the version in data book is that. But again, remember that's cube root, so you can just cube everything instead. Much easier. Okay, and this idea may help you. Basically, the nucleus of atoms is very much like a liquid drop. So a droplet is spherical. If you get into space where you don't have the effect of air and falling and so on, then all water droplets are spherical, perfectly spherical. And if you've ever seen a pond skater, it's to do with that effect that you see there, and it almost has a skin keeping it together, keeping it round. So it's very much like having all your particles inside an invisible balloon, and as you shrink the balloon, it holds them all, it will always pull them all into a perfect sphere, if there's no gravity to affect it. Okay, so that gives us an interesting little kind of idea of what's happening inside. Why would it form into circles? Well, that gives us a kind of this idea, as I said here, of surface tension. How does it work? Well, I've got a bit of a picture for you, but we can work through what's known as the liquid drop model mathematics. Okay, so the basic idea of it is that we can calculate the density of a nucleus. I think the space is on the top of the next page, and we can put that in. So the density is, of course, mass over volume, so rho equals m over v. Okay, please notice that's rho, so that's not our numbers from before. Well, what is mass? Total mass is going to be the number of particles, that's A, okay, multiplied by the average mass of particles, which is signified by the letter U. Now, if we go to the data book, opposite your constants, you've got multiplying factors, and this top one is our value of U. It is the unified mass constant. Now, effectively, that is a multiplying factor. That is the commonality of all particles in all nuclei. Now, ignore the mega electron volts bit at the side at the moment. If you compare it to, can I get them all on? Yes, I can. The values here, they are different. Okay, don't worry about that at the moment. That's because these are lone protons and lone neutrons. When you put them into a nucleus, they actually behave differently. They change mass. Leave that for a while. So the key thing is you can get this unified mass constant. That will apply to your average nucleus particle, any particle in the nucleus, whether it's a proton or a neutron. Okay. Notice they've gone to 4 significant figures there. So they're that secure about it. Okay, put protons and neutrons together in their natural state and they behave in a certain way together. So, well, volume, we've just had that from our previous page, is of course 4/3 pi r cubed. So if we put that together, we end up with our density becoming, and let's just put it all in, I'm going to 4/3 is divided by, so 3 at the top, 4 at the bottom, pi r cubed, okay, and I'm going to put the things together. So I'm going to put r cubed large version at the moment. I'm going to have a, okay, and I'm going to need to introduce a little bit more. So that's our, sorry, I forgot our u there, au. So if we take what we have from before, we can put in the numbers, okay, for radius using a constant and the size of our nucleus. So we are going to cube that, which again goes for the easier version, so proportional to a, but we'll put in the other bits as well. What that means is we end up with 3a times u divided by 4 pi r naught cubed times by a. And obviously a at the top, a at the bottom cancel out, 3u over 4 pi constant. Again, just remind you that's your constant there. So what that means is that this does not vary with atom. All atoms, or all atomic nuclei, have a value of density that is the same. Okay, it does not change. And it's said here, it doesn't matter what you're looking at, it will do the same. And it also gives us exactly the same density, linking back to our last module, neutron stars. Okay, so where everything can collapse to the density of a nucleus, you can stick those numbers in, you will get that. Okay, so you can try that, you can give the value for it if you want, and you'll find that it gives you that thing there. So u, 1.661 times 10 to the minus 27, that was around about 1 and a bit femtometers cubed, so again very large number, etc, etc. So that goes into a fairly consistent number, a consistent number for all nuclei. I should say even the small nuclei that are, shall we say, lumpy. So they may not be spherical, but they actually will still have the same density. Okay, if you've only got 1 proton, 2 neutrons in a nucleus, then it can't be round, can it? It's going to be triangular because there's only 3 nuclei. But why is this happening? It hasn't explained it. It's just playing with the math. So we can use the maths from taking the readings from electron scattering. We can get it into here for different velocities. I should say repeated at different velocities using different voltages to give you different wavelengths, to give you different patterns, to repeat the readings, etc, etc. And what it links to is this idea here, that there is some sort of force holding particles together, just like it does in a water drop. So if every particle has a force between them, then that holds the nucleus together. Effectively, it acts like nuclear glue. So even though these two, for example, are protons and therefore trying to repel, okay, so Coulomb force is trying to split the nucleus apart. If we have enough neutrons, then they will hold the force between them, and the force between them and the protons will hold the whole nucleus together. Okay, and this is known as the nuclear strong force because it's a force in the nucleus and it's stronger than the Coulomb force. So otherwise everything will fall apart, all our nuclei will fall apart. So crucially, it's about having enough of these to hold things together. But what that means is, if we go back to the liquid drop, is that everything's being pulled together. The ones on the outside are pulling each other together, so this force is there and it holds them, and it doesn't matter on the shape, it holds them in a symmetrical shape. And when you get larger and larger, it still forms that symmetry, and it's that causes the surface tension that holds them together. Just like water, it's because they're not being pulled outwards that they don't change their shape. They're spherical. If you drop a water droplet onto something that's not waterproof, then there's a force attracting it to the surface, and your water drop will flatten out. Okay, if you don't have anything that's going to absorb the water or attract to the water, produce forces with the water molecules, then a water drop won't flatten out. So if you get a waterproof clothing and you put water drops on it, if it's waterproof, it will form into little balls. It won't change the shape. It'll just run off the sleeves of your arm, for example. Try it, really impressive. That's how you tell if your clothes are dirty, because if your raincoat's dirty, it's the dirt that causes electrostatic Coulomb force attraction and flattens the shape. So here, for example, if we were to think about 5 nucleons, there's more force repelling than there is attracting. This is unstable, it would fall apart. Therefore, if we had helium, if we have 5 nucleons, then for it to be stable it would need to be helium-5 rather than lithium-5. Okay, so lithium has 3 protons, that's not stable. That's a radioactive, unstable, fall-apartable nucleus. If you've got enough neutrons, then there's enough force to hold it together, okay, and cause the nucleus to be stable. So the nuclear strong force is crucial. How does it work? Well, we've got a graph, of course. And the graph is a really nice kind of layout. If we just think about that on a large scale, okay, we are going to go up to, and it is one you need to know your way around, i.e. you do need to know these numbers. So what I'm going to do is I'm just going to give you a nice even scale going up to 5. Okay, so 1, 2, 3, 4, 5. This is the separation. Okay, this is our value of R, shall we say, in femtometers. Okay, so we're talking about femtometers quite a lot, 10 to the minus 15 meters. Okay. On the vertical scale, we have our forces. Okay, so this is on this scale, again, huge forces, hundreds of thousands of newtons between particles. These are huge forces, incredibly strong forces. So we've basically got 0 in the middle. We have our positive and our negative, and to make that all work, going to go up again to that kind of idea. So obviously this is minus times 10 to minus 15. So here we don't need to know numbers here, but simply what happens. So positive, that positive force goes with those positive charges repel. So repel is your positive, negative for attract. And normally the equilibrium position is a bit less than 1. Okay, so that point there, that separation, a bit less than 1 femtometer, is the ideal distance between all your nucleons. Okay? I'll put it as spacing. It's not the position itself. So, what you'll find is actually this, slightly slopey on mine, this is a very linear behavior here. So if you get a tiny bit closer, if your distance gets a little bit smaller, there is a huge repelling force. The force increases very rapidly. If you pull them a little bit further apart, there's a huge force of attraction, and this linear relationship acts in very much the same way, for different reasons, but the same pattern as Hooke's law. So you can think of these as little springs. Okay, so again, just put in linear, like Hooke's law. Okay, and that separation is proportional to the size of the force. So it will obey Hooke's law on a miniature level. Hooke originally came up with this idea for gases. The reason you could squash them was, again, this force between them, which is true as well, if you can get them close enough together and further enough apart and so on. So, you know, a good educated guess from 400 years ago. Pretty sound stuff. Now, what this does, though, is like Hooke's law. If you pull them too far apart, the force rapidly peaks. Okay, so round about 2-ish, excuse me, that's a bit of a bad curve there. Peaks, and then it dies off before 5. Okay, so what happens is that you will stretch, and then you kind of get your plastic properties, so it becomes weaker, to get to a point at which actually if you get it any further apart the force almost disappears, or rather it disappears very rapidly, so it comes apart very rapidly. So if you can get the nucleons far enough apart, they will fall apart. Your nucleus will be unstable and come apart. But normally the vast majority of isotopes we're working in this area, and it doesn't need to move far for the force to get really big. Okay. Now, I'm just going to change colour, because on top of that, to give you some idea, okay, we have the idea of Coulomb force, which we know is proportional to r squared, so it does give us that curve itself. Now, on Coulomb force, again, it only works if you have two charges, so it'll only work between protons. We do get that inverse square separation. Now, it is on this idea here, I'll do my best to do an inverse square. It is really small. Much smaller than nuclear strong force, around about 100 times, maybe 1,000 times smaller. But if you can get them close enough together, it goes huge. So, at really small separations, Coulomb force is important, but most of the time that controls it is going to be the nuclear strong force. So, Coulomb force, okay, and this one is our nuclear strong force, NSF, that we'll use quite a lot. Okay, so just to make clear, that place, that idea, that round about 3/4, 0.75, 0.8 femtometers is your average spacing. Strongly peaking around about 3-ish femtometers. That's my bad curve. But yeah, that kind of idea. Now, this is the bit that you don't really need that value, but if it gets below there, then you know this effect takes over. So around about half a femtometer is a nice easy way of remembering it if you just remember 5 femtometers. Okay, so if you work that scale, it works much better. So these first 3 sections, okay, the idea of obviously notation, how we found that the nucleus is there, and then going into deeper research methods to find out about what the structure is of the nucleus, has led us into a huge area that we'll now start to explore. Okay, so all about this idea of spacing, and therefore about the density, and therefore what that implies about its structure in terms of density and forces and nuclear strong forces and further experimentation, etc., leads us into the whole of the next 3 chapters. Okay, so really profound ideas, really important. If there is not enough force, then bits will fall off. It's known as radioactivity. Okay, if we can overcome these, and then we can create forces large enough, we could fuse things together. Stars, nuclear fusion in natural processes, as potentially as a man-made process to release energy. But also we can cause these to split as well, so we've got nuclear fusion. So all to do with nuclear power, radioactivity, and looking deeper, a similar structure if we go even more inside, back to my starting thing. So if we repeat that experiment, but instead of looking at the atom, we look at the nucleus, well, we see in the nucleus a bag of particles, particles here. If we go even faster, then we find that each of these particles is made of more particles. And so we can go smaller and smaller and smaller. So the ideas are really profound. The research methods are very similar. CERN is still using effectively, a similar method to this for its research. Stanford University and other linear accelerators are basically doing Rutherford's experiment, just faster. So, big ideas, really useful. Make sure you know your way around this graph, draw it better than me. These are the values you want to use. Okay, so that kind of helps.